Devices and Technology has appointed the following assessment committee to assess the thesis. Research Director Dr. Oliver Klein at the SPINTEC, Speed and Electronics Research Institute in France, and Dr. Grégoire de Loubens at the SPEC, which is the Condensed Matter Physics Laboratory in Saclay in France. And it's myself. My name is Turi Morin-Renos. I'm an associate professor at the Department of Physics, and I've been the administrator of the evaluation committee. The committee recommended earlier that the thesis was worthy of being publicly defended, and the candidate has given his examination lecture earlier today on the following assigned topic, spin electronics. And the evaluation committee has judged the trial lecture to be satisfactory and also to be a very excellent trial lecture. Now the candidate will publicly defend his thesis. And the opponents are Research Director Oliver Klein and Grégoire de Loubens. In case anyone in the audience wants to ask questions, then you have to notify me in the break, which will be after the first opponent's questioning session has been finished. We start with the presentation of the thesis work that Gregor will do now.
So, first of all, I would like to thank the committee members for being willing to evaluate my work and also for coming here today for my defense. I'm also happy to see that so many of you showed up and are interested in hearing a bit about my work. So, during the next half an hour or so, I'll try to give you at least a small taste of what I've been doing for these last couple of years. So this here is a rough outline of my talk. So first I'll try to convince you why magnetism research is important, and I will then give you more of a basic introduction to magnetism and to my field of research on magnetization dynamics. And for those of you who attended my talk this morning, some of this introductory material might be quite familiar, but then you can just regard this as a sort of a quick recap. So following this basic introduction, I then want to go into more of the specific details related to my PhD work, and I'll then end my talk with an outlook and some final considerations from my PhD studies. So I thought I would start with an example which is probably familiar to most of you, which is that of magnetic memory. So as an example here, I've shown the advancement in the storage capacity of the iPod. So we see that there's roughly a doubling in the storage capacity about every 1 to 2 years. So this advancement in magnetic data storage is one of the examples where magnetism research and nanotechnology has been making a huge impact on our technology. So magnetic memory in your computer is based on this set of very small magnets, where the information is stored through the direction of the magnetization, here indicated as up or down. And the routing of information is based on this write head over here, which can then be used to switch the orientation in these magnetic regions. And the information is then read out to the read head on this side, which is then converting the direction of the magnetization here into a signal of ones and zeros representing the bits of information. So the advancement in our magnetic memory storage has been based on shrinking the size of these components. So this enables more information to be stored in the same area. But a problem about this shrinking process is that as you keep reducing the size of the devices, it is becoming increasingly difficult to reduce them further. And due to this, being able to understand how these magnetic phenomena might behave when they're confined to the nanoscale becomes important. So this is one of the current applications of magnetism research. So what should we be interested in research on magnetism? Well, one thing is that it can be useful for several nanoscale magnetic devices, and research on magnetism could also be useful for developing future devices for memory and computation based on magnetic phenomena. But also on a more personal level, I will have to say that the main motivation is probably curiosity-driven, in the sense that as physicists we tend to be very curious people and we really like to understand how stuff works. So I hope these previous slides has convinced you that magnetism research is important. But before going into any more specific details of my PhD work, I'll first give you more of a basic introduction to magnetism and to my field of research on magnetization dynamics. So first of all, we have the electrons, which are the charged particles that make up what we know as electric currents. And in addition to these charged properties, the electrons also has a property called spin. So in a very simplified picture, these electrons spin give rise to a small magnetic moment, which is at the origin of magnetism. So if we first consider now a normal metal, as indicated here to the left, these electron spins tend to all point in random directions, and there's no net magnetization in the material. If you now consider a ferromagnet, like shown here, due to the exchange interaction between the electrons, this tends to lock these spins together to point in the same direction. And this exchange interaction is the fundamental force behind the magnetic order. So in a very simplified picture, we can say that a ferromagnet is a material where all these electron spins are aligned in the same direction to produce a net magnetization. So this is probably what most of you think of when you hear the word magnet. So having introduced now the ferromagnetic states, I now want to continue more onto magnetization dynamics, which is getting closer to my actual research. So and then I want to begin with the simplest case and consider a single electron spin in a magnetic field. So in a magnetic field, this will exert a torque on the magnetic moment, which causes a precession motion of this magnetic moment. And this precession motion can be described by the equation here, but it's perhaps easier to visualize through this brief video clip, where we see the magnetic moments indicated by this green arrow, showing a precession motion around the magnetic field. And so here, this precession of the magnetic moment in a magnetic field is the governing principle behind several important experimental techniques. And in particular, ferromagnetic resonance is very important for the work done in my thesis, so this is something I'll get back to in more detail in a couple of minutes. But of course, a ferromagnet doesn't consist of a single electron spin. But as an approximation, let's now consider that the ferromagnet shown here can be seen as a collection of all these spins contributing to a total magnetization M. And also, in a realistic system, there will be some dissipation of energy and damping during this precession motion. And this is similar to, for instance, that if you have a pendulum swinging back and forth, due to friction, this will cause loss of energy, and this pendulum motion will eventually settle down. So this effect of this damping term can be probably easiest visualized through this video. So we see that, as before, the magnetization will precess around the magnetic field, but this dissipation of energy, described by this damping term here, acts as a form of viscous damping force that pushes this magnetization into the direction of the magnetic field. But I also want to note that the magnetic field here is not only the applied magnetic field, but it also includes contributions from various anisotropies in the magnets. But this is something I'll talk more about later. So this precession of the magnetization will have a certain frequency. And this depends on several parameters, such as the size and shape of the magnets, the strength and orientation of any applied magnetic fields, as well as material parameters such as the saturation magnetization. And if we then apply a small perturbing microwave field similar to this characteristic frequency, this can induce a precession motion of the magnetization where all these magnetic moments, as shown here, will start to oscillate in phase. So this illustrates the phenomena of ferromagnetic resonance, which is the governing principle behind the main experimental technique that I've used in my research. So experimentally, fMR spectroscopy can be performed by placing a small piece of this magnetic sample within this kind of microwave cavity. And here at the sample position, there's a small oscillating magnetic field with a frequency determined by the type of cavity that you have used. So, as we saw in the previous slide, this precession frequency of the magnetization is given by the effective magnetic field. So this means that if we now apply an external magnetic field, we can adjust the resonance frequency of the sample. This is indicated by this red line here. So we then see at a certain magnitude of this applied field, this precession frequency of the sample will overlap with the frequency here of the microwave cavity. And when these frequencies overlap, the microwave field in the cavity will induce a precession motion of the magnetization in the sample. And experimentally, this can be observed as an absorption of the microwave power in this cavity. And this is also illustrated here, where we see that at a certain magnitude of the magnetic field, we see this characteristic microwave absorption line shape. So, as the resonance frequency depends on the effective magnetic field, this means that fMR spectroscopy can be used as an experimental technique to probe magnetic states. So, by performing these kind of fMR experiments, one can then extract various parameters such as saturation magnetization, characterize various crystalline and shape anisotropies, obtain important material parameters like the magnetic damping and so on. So this means that it's quite a versatile technique which can probe both the static and the dynamic properties. So after providing you with this more of a general introduction, I want to continue with more specific details from my actual PhD work. So my goal then is to compress a PhD worth of research into about 20 minutes, so I will not have very much time to go into all the details. So the main research topic of my thesis has been on the magnetization dynamics in various systems, ranging from thin films to confined magnetic elements on a nanoscale. And the main techniques I've used in my research is fMR spectroscopy, which I just introduced, as well as some numerical simulations and simplified analytical models. So one of the important topics I've been working on is this damping of the magnetization precession. So a low damping represents less dissipation of energy and is favorable for many dynamical applications. So due to this, the search for material systems with a low damping is an important field of research. And another concept which is also important in several of the projects I've been working on is how the effective magnetic field will govern the magnetization dynamics. So this is the first topic I'd like to talk more about. So in introducing the effective magnetic field, I first want to introduce the main magnetic energies. So in general, the magnetic energy of a system will consist of several contributions. So the first number here is the exchange energy, which is associated with this exchange interaction I mentioned initially, which is this fundamental force behind the magnetic ordering. But there are also several other important contributions, such as the magnetocrystalline anisotropy, which favors the spins aligning along certain crystallographic directions in the material. We then have the Seemann energy, which describes the coupling to any external magnetic fields, and we have the demagnetization energy, which depends on the size and shape of the sample. So I will not have time to go through all these contributions in detail, so the important thing to consider for now is that they all contributed to the total magnetic energy of the system. So as an example, let's now consider this system shown here to the left. So here we have a magnetic sample with the direction of the magnetization shown by this red arrow here, given by these angles theta and phi. And in the figure on the right, we have the corresponding magnetic energy for the system. And in this figure here, the blue regions represents a low energy and red a high energy. So from this we see that there are some orientations of the magnetization which result in lowering the magnetic energy as given by these angles theta and phi. So in the example here we see that one of these energy minima is located at an angle of theta equals 90 degrees and phi equals 0 degrees. So from this figure to the left, we see now that this corresponds to a magnetization or being oriented in the sample plane and along the long axis of this ellipse. So this means that by calculating the magnetic energy of a system, this could provide valuable information about the magnetization. And in addition to the static orientation of magnetization, the magnetic energy can also provide valuable information about the dynamical properties. But as a more simplified illustration of this, let's first now consider this system I've shown here to the left. So we here simply have a box with a mass m connected to a spring. So if we now stretch this spring by simply pulling this box to the side, we will increase the energy of the system according to this energy potential. And if we now let go of the box, this spring will pull it back and it will start to oscillate back and forth, as also indicated here if we plot this box position versus time. So the frequency of these oscillations back and forth will now be determined by the shape of this energy potential as shown through these equations here. And this is similar to the case we have also in the magnetic system, although the energy potential is in this case a bit more complicated. But if you now give the magnetization a small push away from its preferred orientation in one of these energy minima, it will be pulled back and start to oscillate around this equilibrium orientation. And the frequency of these oscillations, which is the ferromagnetic resonance frequency, is also in this case determined by the shape of this energy potential, as shown through this slightly more complicated equation here. So this means that if we can control the magnetic energy landscape, we can also control the dynamic properties. And this is the main focus in paper 4 of the thesis, where we showed how we can use a combination of crystalline and shape anisotropies to control these magnetic energies, and by this control the dynamic properties. So as a model system, we considered samples made from epitaxial iron films, and this results in a system having a fourfold crystalline anisotropy, which favors the magnetization oriented along one of four equally preferable crystallographic directions, shown here. And the shape anisotropy is now determined by the size and shape of these magnetic elements. And in our case, we used elliptical samples of various sizes. So one of the conclusions from this project was that we showed how we can use the size of these samples to balance these contributions from the crystalline and the shape anisotropy, and then use this to control the magnetic energy landscapes, which then enables tailoring the dynamic properties. So this ability of tailoring the dynamic properties is a feature which might be interesting in some applications. But another important parameter when it comes to the dynamic properties is this damping of the precession motion. So this damping is now the next topic I'd like to talk about. Applications. So searching for materials with low damping is an important field of research. And as I mentioned, this fMR spectroscopy technique can be used to control or to measure this magnetic damping. So as I showed you previously, this characteristic microwave absorption line shape associated with the precession of the magnetization in the sample will here have a certain line width. And this absorption line width depends on the magnetic damping in the system. So we can see that this line width has two main contributions. So we have one term that is independent of the precession frequency, and then this other term which is proportional to the precession frequency and to this damping parameter alpha. So this means that by measuring this absorption line width, we can now use this in order to extract the magnetic damping. And an example of this is shown in this figure here to the right, where I plotted the measured line width versus the microwave frequency. And from this linear relation between line width and frequency, one can then extract this damping parameter alpha from the slope of this line here. And this example is taken from paper 1 of the thesis, where we investigated the magnetic damping in thin LSMO films. So LSMO is a ferromagnetic oxide material which has several interesting material properties. So it has a Curie temperature above room temperature, it has a near 100% spin polarization, and the magnetic properties are also very sensitive to the structural parameters. This means that by compressing or stretching this film by growing it on top of or sandwiching it between different materials, we can then use this in order to engineer the magnetic properties. But the main parameter we focused on in our work was this magnetic damping. So in our study, we obtained a minimum value of this damping parameter of 0.002. And although this specific number probably won't tell everyone that much, this means that the damping is among the lowest recorded for metallic ferromagnets. And this low damping, in addition to the other interesting material properties, indicate LSMO as a very promising material for further investigations. So, having discussed briefly now some material-specific properties of magnetic thin films, and I want to continue on to a more general feature, which includes how the effective microwave field can affect FMR excitation. And an effect which might influence this is that of induced microwave eddy currents when you have conductive samples. So the next topic I'd like to talk about is eddy currents. So this is induced currents that flow within conductors according to Faraday's law. And here on the right we have a simplified schematic of a current loop enclosing an area A. And if we now have a time-varying microwave magnetic field, this will now induce a circulating current flowing in this loop. And but the magnitude of this current depends on several parameters, such as the size of the current loop, where a large area will increase induced currents. We also have the frequency of the microwave field, where a high frequency will increase the current amplitude, and also the angle of this microwave field with respect to the loop plane. So having this field perpendicular to this loop plane will maximize induced currents. So the interesting thing or important thing in the context of FMR is that these induced currents will now give rise to an additional magnetic field in addition to the applied microwave field. And in general, this extra contribution will have a certain phase shift with respect to the applied microwave field. So this means that the total microwave field acting on the ferromagnet will now consist of two contributions, where we have the applied microwave field and this induced microwave field here. So that this microwave field has several contributions, can have some important effects on the FMR excitation. And one example is so-called microwave screening effects, where these fields can actually compensate and partially cancel out the applied microwave field. And by this effectively reduce the amplitude of the magnetization procession. And as the magnitude of these induced currents depend on the sample and field geometry, we can then use this in order to control the impact or magnitude of these currents. So let's first consider the case where we have this microwave field applied parallel to the sample plane, where we should minimize the amplitude of these currents. And one would then assume that this microwave absorption associated with the precession of the magnetization in the sample should scale with the size of the sample. And this is also what we see, indicated by these blue data points here. But if you now change the field geometry such that we have this microwave field applied perpendicular to the sample plane, and by this maximize these induced currents, we now see something different. So in this case, we see that as the sample size is increased, the amplitude starts to drop. And this is attributed to these microwave screening effects, where the induced fields from these additional currents partially cancel out the applied field. So this indicates that there's quite a significant screening effect, also for this case of very thin samples, which is in contrast to what is usually assumed about these eddy current effects. And in addition to these screening effects, another impact of these currents is that they might influence what is called the FMR line-shape symmetry. So this line-shape symmetry is not something I'll have time to discuss in detail now, but the important consideration is that this line shape symmetry parameter is something which is often used in experiments to analyze experimental results. And due to this, it becomes important to consider any effects that might influence this line shape in order to not draw any wrong conclusions. So, to summarize for now this discussion on eddy currents, our findings indicate that this could be important to consider also for very thin samples, but these effects are usually neglected. So, wrapping up for now the discussion on eddy currents, it's time to move on to the final topic of my talk, which is something called spin torque oscillators. So these spin torque oscillators are nanoscale magnetic oscillators, which are interesting for several prospective applications as microwave sources or for signal processing and telecommunication technologies. And these spin torque oscillators are based on or driven by the spin transfer torque effect, which is illustrated here. So if you have initially an unpolarized current flowing through a magnetic layer here to the left, this current will now become spin polarized. And when this spin polarized current flows into the magnetic layer here to the right, it will now transfer spin angular momentum, acting like a torque, trying to align the magnetization in this layer in parallel to that in the left layer. And I don't have time to cover the spin transfer torque in detail now. So the important thing to consider is that this spin transfer torque can be used to control the magnetic states. And this is the driving mechanism of these spin torque oscillators. So to the left here I have a simplified schematic of a nanopillar SDO, which consists of a magnetic fixed layer here at the bottom, acting like a polarizer layer, and then a magnetic free layer here on the top. So by running a spin polarized current now through this stack, this will now exert a torque on the magnetization in the free layer, which can cause a precession motion of the magnetization. So this means that by running a DC charge current through the stack, we can now obtain a microwave signal as output. And this is an attractive feature for applications where it could be used as, for instance, microwave oscillators. But for applications, having a single one of these oscillators is usually not sufficient. So the ability to fabricate arrays of these oscillators, which all oscillate at the same frequency, is important. But a problem is that from the fabrication process, these oscillators tend to oscillate at slightly different frequencies. So the interesting thing in this context is the ability of these SDLs to synchronize to one common frequency. So this is what we have been studying. So the type we have considered is a so-called vortex-based SDO, which consists of this polarizer layer at the bottom and a magnetic free layer on the top with a so-called vortex ground state. And the direction of the magnetization in this free layer is also shown here to the right, where we see a curling magnetization here along the edges of the disk, and then this small black region at the center representing the vortex core with an outer plane magnetization. So the fundamental mode for the system is now a gyrotropic motion of this vortex core driven by a spin polarized current through this spin transfer torque effect. And this can be illustrated by this video here. So the interesting thing now is the ability for these SDOs here to synchronize and settle in a coherent state. And in order to synchronize, these oscillators need to interact with each other. And the approach we have considered is the interaction through the magnetic dipolar fields produced here by the individual oscillators. So if this interaction is sufficiently strong, this may now cause a synchronized and phase coherent state between these oscillators. So what we have been mainly focused on in our work is what happens when you scale up from a small system with few oscillators and now consider large arrays of coupled SDOs. So for these SDOs to synchronize, they need to interact with each other with a certain minimum interaction strength. And one of the things we found in this study was that this critical interaction strength also depends on the number of oscillators. And one of the things we found is this finite size scaling indicated in this figure here. And here you see that for an interaction strength lambda, which is here, in our case, determined by the spacing between these oscillators, there also exists a corresponding critical system size n, which then marks the maximum number of these oscillators that can be synchronized given this interaction strength. So this indicates that this collective behavior when you scale up to large areas of these coupled SDO is something which is important to consider. And there are, of course, several more things I would like to tell you about this and also other projects, but time is starting to run out for this presentation, so it's time to just go through a quick summary of some of the main results. So in the project on these LSMO films, we found a fairly low damping parameter, which is among the lowest recorded for metallic ferromagnets. And this low damping, in addition to the other interesting material properties, indicate LSMO as a promising material for further investigations. And regarding the eddy current effects on FMR, we found that this is an important effect to consider also for very thin film, which is in contrast to what is often assumed about these kind of effects. But rather than considering this simply as a parasitic effect, we can also start to thinking of ways how we can use this in order to engineer the microwave fields in a possible device. So on paper 4, we showed how we can use a balance between crystalline and shape anisotropies to control these magnetic energy landscapes, and by this being able to tailor the dynamic properties. Where this ability of tailoring the dynamic properties is something which might be of interest for some applications. And in the final project on these feedback oscillators, we found that this synchronization is purely a finite size effect. So perhaps the main conclusion is that this complicated collective behavior, when you scale up to large areas of these coupled oscillators, is something which needs to be considered. So as a final outlook from my PhD studies, I would like to emphasize that new advances in science is really a team effort. And continued progress is building upon the knowledge obtained from previous research. So as research often tends to answer some questions, they also tend to generate new ones. So in this sense, I hope that the research that resulted from my PhD studies will prove to be useful for fellow scientists and also spark new ideas for future investigations. So there's still a lot of open questions and problems to solve, so I don't think we'll run out of things to do quite yet. So I mentioned that research is a team effort, so in my final slide I would just like to thank all the people that have been involved in my research in some way or another, and much of the work would not have been possible without their contributions. So I hope that through my presentation today I have given you at least a small basic insight of what I've been doing this last couple of years. So with this I would just like to conclude my talk and thank you all very much for your attention.